Welcome. Here's the fourth lesson on aromatic chemistry, subtitled Friedel-Crafts acylation. So we've got a starter activity again. Pause the video and have a go at this. It's all practice of stuff from last lesson and also from year 12. So then, things that we should be arriving at. Equations show generation of the electrophile. If you did the two versions that kind of combine to make this, that's alright, but it is better to just do it in one go. So there we go. Electrophilic substitution mechanism. The only sort of wrinkle here is it's chlorobenzene. You have to be careful about where you put your nitro group because I wanted to make 4-nitrochlorobenzene. There you go. Then your year 12 stuff. Aluminium chloride AlCl3 is trigonal planar. If you're wondering how to arrive at that, go and watch a video about shapes, how to deduce shapes and electron pair repulsion theory, but the short version is aluminium has 3 bonding pairs and no lone pairs, therefore it's trigonal planar with 3 bonding pairs spaced equally out at 120 degrees to one another. Then Al2Cl6, which is what that thing is, has a slightly complex looking kind of structure. It's probably on the upper, limits of what you'd be asked when you do coordinate bonding at year 12, because it forms 2 coordinate bonds in a sort of slightly strange arrangement to do with the chlorine atoms and the space for 2 electrons on the aluminium. When that happens, each aluminium, each separate aluminium then has 4 bonding pairs around it and no lone pairs, so that changes the shape. It's no longer trigonal planar, it's now tetrahedral at 109.5 degrees. You can see in my image on the right that I didn't bother trying to draw all the things attached to the aluminium because it just gets a bit complicated with this, what we call dimer structure, the 2 molecules stuck together. But the point is still the same. You've got 4 bonding pairs around the aluminium now. One of them is a coordinate bond, but it's still a bonding pair. Right then. On to the start of this lesson. Here are the facts. We learn about a reaction called Friedel-Crafts acylation, which involves the addition of acyl groups to benzene and benzene derivatives. Now, we've already done some stuff on acylation, right? So it's important to point out that acylation is a type of reaction. It is not a mechanism. So this is not going to be the same reaction as the nucleophilic addition elimination mechanism that we do when we're talking about reaction of acid chlorides with nucleophiles or acid anhydrides with nucleophiles. It is still acylation though. It is still a way of adding an acyl group to something. So this is useful because it adds carbon chains as substituents onto the ring, and something that we'll look at in a later consolidation lesson is that alkylation is also possible rather than acylation. More on that later. So sticking with acylation and sticking with acyl groups, here's a little task. Think about the acyl group, what it looks like. Draw an acyl group attached to a leaving group, which you can mark as Z. In your diagram, distinguish between which part is the acyl group, which part is the alkyl group, and which part is the carbonyl group. And then give 2 examples of acylating agents. So pause the video and have a go at those questions. Okay, so keeping sort of consistent with the stuff that I was doing in the acylation lessons, right? We've got this image of RCOZ, and then I've kind of ballooned several colours around it. So the green part is the acyl group, RCO. The yellow part is the leaving group, which is the bit that gets basically kicked out of the molecule when the acyl group is transferred to something else, and whatever it's being attached to is then in the position where Z was. The red part is just a carbonyl group, and the thing represented by R, we didn't do this much before, but it is called an alkyl group. So that'll be CH3 or CH2CH3 or CH2CH2CH3 and so on. Some kind of hydrocarbon chain of varying length. Usually just CH3 most of the time at A level. So then, two examples of acylating agents. First one is acid chlorides, for example ethanoyl chloride. Second one is acid anhydrides, for example ethanoic anhydride. So that's lots of stuff that we knew already, and a lot of that's going to be useful even though the mechanism for this acylation is different. So then, kind of like with the nitration reaction, let's have a little look at the reaction mixture. We're going to be looking at mixing an acid chloride, which is the source of our electrophile, which is called an acylium ion. That's what this thing is called. That's going to be mixed with an aluminium chloride catalyst, and that needs to be kept away from water so the conditions are anhydrous, and the conditions are also going to be dark. So then, we need an equation to show generation of the electrophile again. We've got any acid chloride being mixed with aluminium chloride, and we're making an acylium ion, so you need to try and deduce what the formula of the other product is. So thinking about it, you should be able to work this out. It's going to be a negative ion, right? Because in chemistry, if you've made a positive ion, you must have made a negative ion as well, right? You can't have one without the other. The other thing you should work out is that there's a chlorine missing from your acid chloride, and that chlorine needs to have gone somewhere, and the place that it has gone is it's now attached to aluminium chloride. Just to tidy this up a little bit actually. Just because this is an aluminium ion, it's often put in square brackets. It's not essential that, but it is usually the way that it's drawn. So your aluminium chloride has picked up a chloride from ethanoyl chloride and formed AlCl4-. The reason this is important is that thing can now act as an electrophile in our reaction. So let's have a look at how that works. The mechanism type is the same as in the nitration reaction, so it is still electrophilic aromatic substitution. What I've done this time is I've set up all three steps, and what you need to do is copy them and put the relevant curly arrows on. You should know how to do this if you've done the lesson on nitration and done a bit of practice on that. So we've got a curly arrow from the delocalized ring of electrons onto the positive carbon. We've got the delocalized ring of electrons reforming by using the bonding pair between the carbon and the hydrogen. We then have our acylated aromatic product and a hydrogen ion on the right. So I think that's actually comparatively straightforward. There are lots of complications in the aromatic topic, but that's stuff we'll talk about in the next video. I actually think the mechanism is reasonably straightforward. Something else that we should point out is that the aluminium chloride needs to be regenerated for it to be considered a catalyst. We saw this a little bit before with the sulfuric acid in the nitration reaction. All I want you to do is to work out the formula of the byproduct, and again it should be obvious if you look at it for long enough. So you get your aluminium chloride back by a hydrogen ion reacting with AlCl4-. Byproduct is HCl. Right then, on to the practice. So just to be clear about what I want you to do here, right? I want an equation to show the generation of the electrophile. I want an electrophilic substitution mechanism and an equation to show regeneration of the catalyst. So those are the three things that you need to do in each of these three examples separately. So the first two examples are benzene and ethanoyl chloride. So you do those three things for that combination. Then methyl benzene plus ethanoyl chloride to form this thing. I've drawn the picture rather than naming it because it just gets to the point where it's a bit silly. And then finally, bromobenzene plus propanoyl chloride to form this thing. So there's plenty to go out there. 3 different acylations of aromatic rings. Remember, you need to do all 3 of those things for each of these examples. So once you've had a go at that, we can have a look at the answers. Here's how it looks for the first one. This is very similar to what we did in the example, it's just that I've made it ethanoyl chloride instead of a generic acid chloride. Doesn't matter where you've attached it, by the way. It's ended up in the, on the right hand side in my mechanism. It doesn't really matter. So if you've got your acyl group added at the very top or at the very bottom, in this molecule it makes no difference because it's just a plain old benzene ring to begin with. So then we've got ethanoyl chloride and methylbenzene. This time it does matter where you add your acyl group because I asked you very specifically in the starting point for the methyl group and the acyl group to have those positions relative to one another. So make sure you're happy with that, make sure you're not making silly mistakes. Finally, we've got propanoyl chloride reacting with bromobenzene. Again, position of the acyl group does matter here, okay? And also the equation would be different because it's propanoyl chloride, not ethanoyl chloride. So there's your equation at the top. There's your mechanism below, including the sort of final product. And then the equation to show regeneration of the catalyst is the same actually in all 3 examples. That's it.